And yeah, let's just go ahead and dive in. So we're going to be talking about machine learning on time series data. And this is a topic that's near and dear to my heart because time series data is all around us. It's everything from sensor readings to commodity prices, signals that are taken from audio, video, medical devices, everything. And so being able to properly process and deal with this kind of data is not only useful, but also quite challenging, especially because time series data tends to be quite large in its processing requirements, especially if you're dealing with sensors that sample very quickly, like, for instance, a software-defined radio, which can generate gigabytes of data per second. And so being able to efficiently and flexibly deal with time series data is critical when you're working in one of these fields. Just as examples so that we're all on the same page, there are many, as I said, many different data sets that we could take a look at or try and process. I actually have two example data sets that we'll be looking at specifically today. We have one that is a oil price over time time series, where you can see here over, let's say, about 400 months, we have the price of a crude barrel of oil. And we also have one that's like a daily minimum temperature over time for a particular location. Where over the course of days, you can see that the temperature fluctuates up and down. I should say that that daily minimum temperature, the x-axis is actually incorrect because I downsampled the data so that we would have roughly the same amount of points in both. So it's not actually days anymore. It's actually like tens of days or something like that, which is why the yearly cycle looks like it's cycling a little bit too quickly. So when we're working with time series data, there's many different ways that we can do it. And spoiler alert, we're going to be using machine learning. We're going to be using Flux and the capabilities of Zygote and all those packages that we've been building up in the Julia ecosystem. But before jumping to machine learning, there is a large wealth of tools that exist that you can use to solve problems. Things like, how can I isolate this particular component in my time series? How can I look at slow fluctuations versus quick fluctuations, filtering based on frequency and things like that. Looking at the composition of fast and slow changes or high and low frequencies. And there exist many packages to help with this. Things like timeseries.jl, dsp.jl, wavelets.jl. Each of these is a different tool that could have a webinar on its own and has a rich wealth of literature behind why it is useful and what it can be used for in order to extract features from your time series and process it efficiently. But occasionally we want to do something new or unusual, something that doesn't fit inside the box of the signal processing literature that already exists. And for those kinds of tasks, or for tasks that are just mind-numbingly large in their in their hubris, in their desire to analyze the world, we usually reach for machine learning. And the reason for that is because when we use machine learning, we don't have to specify each individual piece of the processing pipeline. We're able to kind of specify the overall shape of what we want the processing to do. And we kind of assert that that shape is going to be able to succeed at whatever task we give it. And then we just use the machine learning tooling to try and learn the proper parameters for the computations that we're applying. And so we're going to talk about two main approaches here in terms of machine learning. We're going to talk about feed-forward architectures and recurrent architectures. And we're going to apply both of them to time series data. And we're going to see how they are able to successfully complete some tasks and not very successfully complete other tasks. So really quick, a feed-forward architecture is something that looks like this. So if I have a time series x and it's stepping through time, so I have x of t minus 1, x of t plus 1. A feed-forward architecture means I take only those pieces of data, I mash them together in things that are often called hidden layers, or you may, that's maybe a little bit dated because now we have many layers in our models, so we don't tend to call them hidden anymore. But Anyway, we start from our inputs, we mash them together. And by mash them together, what I really mean is we do essentially a matrix multiplication and then pass it through what's called an activation function, which is just a nonlinearity. And we do that again and again and again until we get outputs. Now, the kind of task that you can try and solve with this is quite varied. You can have a regression style task where I have a time series that's coming in and I want like something that looks like a time series coming out. So an example of that would be prediction. I give it the last 3 time points and I want to predict the 4th time point. Or I give it the last 3 time points and I want it to predict the 10th time point. Another example would be classification, where I give it 10 time points and I say, is this an example of class A or is it an example of class B? Just to give kind of an example of something that you might do with this, my PhD thesis actually was on classifying cough signals. So it takes a cough signal, it analyzes it, and it tries to determine, is that a cough that's caused by tuberculosis or a cough that's not? It's something else, pneumonia, the common cold, whooping cough, that kind of thing. Another example of classification is if you hear a sound, is that a cough sound or is it a door slamming or a car honking or something else? And so that's an example of classification, where something like regression would be, again, you have a time series in, you want a time series out. So a feed-forward architecture is one where you have the inputs and they are connected in this example where all the arrows are always pointing to the right. There's nothing that goes backwards. There's no loops or anything, which is in stark contrast to a recurrent architecture. So here we have x's at the bottom instead of on the left, and they're feeding upwards. But you see on the left, this blue H has a connection back to itself. And what that means is if I feed one data point into this H, I can then stop feeding data points in and H will continue to output things to the output, which is called O here, again and again and again and again. So there's kind of this internal machine inside of H that allows it to keep on processing time step after time step. I can keep on feeding in new X's, as we see here, where this H kind of evolves along with the input. And so this is called a recurrent neural network, and it's used to have kind of an internal state that kind of spins up and stores data inside of it, and we can continue to ask it for more and more outputs over time. This one is particularly interesting when dealing with time series data because all of the X's before, X t minus 1, t minus 2, all the way back to t minus 1,000 if we want, all of those X's can contribute to the state that's inside of H. And so these recurrent architectures are able to have kind of a long memory. They're able to remember the things that they've seen in the past and use that to their advantage in giving outputs in the future. And so oftentimes we like to use these kinds of recurrent architectures when we're dealing with signals that have long time dependencies inside of them. Kind of thinking backwards on the data sets that we saw before, an example of this is the daily minimum temperature over time. When I'm at this point, the value that I have here is very related to the value that's, 1, 2, or 3 years ago. There may be some variation, right? Maybe this is slowly going up over time or whatever, but there's a lot of correlation between days that are separated by, a year. Whereas in, say, oil price over time, there's not much correlation. It's when we're going up very quickly here, we'll probably keep on going up, but then we may go down immediately after. So there's not as much correlation here as there is here. And so we call these long-term dependencies. And these long-term dependencies can be exploited by something that has the memory to reach backwards in time and use the information from back then. I'm going to really quick break out of this and make sure that I can't see the questions very well. So Eric is going to shout out if there are questions that I should answer before continuing. But I really do encourage you all to ask questions as we go. Especially once we start getting to code and are no longer just looking at flowcharts. So the kind of machine learning that we're going to be doing today is called supervised machine learning, which means that we know the correct answer with our training data. So as an example, if we were trying to predict the next time point from previous time points, we know the correct value for the next time point. And so we're able to kind of explicitly tell the network, okay, the guess you made was wrong. It needs to be pushed in this direction. And so the way that we'll do that is we'll collect our data into batches. We'll push these example data batches through, and we'll calculate what's called loss. Loss is how far we missed the mark. If we're doing regression, it's as easy as just subtracting the value that we predicted from the actually true value. And then once we have that loss, we'll use gradients, which I'll explain in a minute, to adjust parameters inside of our model to reduce that loss. So if we predicted 2.5 and we needed to predict 3, then we will do whatever needs to be done in order to cause our model to predict something a little bit higher. Maybe not all the way to 3. Maybe we'll predict 2.6 next time. And then we'll iterate again, and we'll predict 2.7 the next time, et cetera, et cetera. And we keep on repeating this many, many, many times. Now, as I was alluding to, we take our input data and we're going to push it through some kind of processing. Now, I'm intentionally being a little bit vague about the kind of processing we're doing, because this is what we call the network architecture. It's the shape of the computation that we're going to do. And I'll talk about that more once we have actual solid code in our hands. But in general, it's going to be things like matrix multiplies and applying nonlinearities, things that allow us to fit nonlinear behavior in our models. Now, this processing has certain parameters that are inside of it. And once we have finished processing our input data, we get our output, which we can compare to our true output. Because again, this is supervised machine learning, so we actually have a true output for each of our input examples. From the output and the true output, we'll be able to calculate error. And the error is going to be propagated backwards using the gradients that we will calculate using, using the Flux and Zygote packages in Julia, in order to give ourselves the updates that we need to apply to our parameters. And we do this over and over and over again in a loop until our output and true output get as close as possible to each other. All right, now that we understand the general idea of what we're going to be doing, let's go ahead and dive into some code. So I'm going to switch over to my VS Code instance. And again, feel free to ask questions. So in this VS Code instance, I am going to have a couple notebooks that I've written that go through and demonstrate some of the capabilities. And I'm basically going to walk through them, and we can adjust parameters and see how the behavior changes and all that good stuff live. The first thing we're going to do is we're going to just take a look at some of the data that we have. So I'm going to be using the WGL Maquis package, which is it's a version of Maquis, which is a graphing library that runs using WebGL. The reason I'm doing that is because inside of VS Code, it allows me to have interactive plots. So I'm going to clear all the plots, load my data sets, and we'll take a look at that oil price data set. And of course, I need to restart my session because of course that's what always happens when you start running a live demo, is something's broken from what you were doing before. So we'll load WGL Maquis. We'll load our data sets, which by the way are basically just free CSVs from online with a little bit of processing to load them in the right format and such. All right, and then we will plot our oil price data set. So WGL Maquis is going to bring up a plot over here. It's going to basically just plot the data as lines, give it some axes, etc. And the nice thing about WGL Maquis is that it's interactive, so I can zoom in and I can look at it. I'm not entirely sure how well the plots are going to show up in the video, so I may zoom in with the macOS zoom command, and we'll see if that works well. And here we have the dreaded time to first plot in Julia. Luckily getting better with every release. So as I said before, we have our oil price data set and our minimum temperature data set. The minimum temperature data set is going to be the one that I'm going to be focusing on because, spoiler alert, it's much more learnable because there's a lot more correlation in there. If I was actually able to properly predict oil prices based on previous oil prices in a 1-hour webinar, I think I may have a different job. But fortunately, for me, it's quite difficult because it's quite random.
Elliot,
You would need a lot. Yes.
while we're waiting for the data set to load here, there was a question. What's the include command?
Oh, great question. So include basically means copy paste this file into here. So you just loads this file. So I have this datasets.jl file here that has a bunch of useful definitions. So if I open this up, this has things like get CSV dataset path, oil price dataset, etc. So all this code that I've written to do things like load the oil spot price.csv file, all that stuff is included in this datasets.jl file. And then inside of my data exposition file, when I run this, it just loads in all that code and runs it. So it allows you to kind of sort of copy paste all that code into here. All right, so we've got our oil price data set. We can do things like zoom in and take a look at things. Really quick, if I zoom in on it like this, does it get easier for you guys to see? Or do you not see me zooming in at all?
Nope, we see it.
All right, great. That's great. All right, so this is our oil price data set. We also have a minimum temperature data set, again, which looks quite cyclical in nature. So we feel there's a good chance that we should be able to predict something. You know, if I've seen the last 3 years and you ask me what it's going to be like next year, I should be able to give a reasonable answer. So with that all being set, let's go ahead and start looking at some machine learning. So what we're going to do is we're going to start with a feed forward approach. So again, this means that we'll have kind of a window of time. And what we're going to do is we're going to take a window of time and we're going to try and combine the data from that previously known window to predict some point in the future. So again, we're going to start with our minimum temperature data set. I'm going to just run these things again to include the pieces of functionality that I need. I'm going to close these plots. It's going to plot the minimum temperature again, just so that we know which data set we're using. As you can see here, we can switch between using the oil price data set or the minimum temperature data set at will. And what we're going to do is we're going to build a model using functions from Flux. And so here is where we get to talk about what the processing actually looks like. Now, we use this thing called chain, which basically just allows us to stack layers on top of each other. And each layer is going to be defined with a particular shape. So here I am saying I want a layer that takes in so many time points and gives out so many time points. Here I've defined analysis window to be 10. So this means that we're going to look at the last 10 time points. And this first layer is going to mash them up and spit out 10 more data points. Then we give it to another one, which will mash those up and spit out another 10 data points. And then finally, we'll have one that takes in 10 data points and spits out 1 data point. So if we were to draw this, switching back to my keynote, looking at the feed-forward architecture, this looks like we have a stack of 10 bubbles here, connected to another stack of 10 bubbles, connected to another stack of 10 bubbles, and then it all points to one bubble coming out. Now, each of these dense functions, what it actually creates is it creates a matrix that will be, in this case, a 10 by 10 matrix that mashes our data points together. And basically, this allows the network to find correlations and relationships between the data points. And specifically, what it's going to do is it's going to find relationships between these 10 data points and the desired output. Now, we haven't defined what our desired output is yet. All we've said is this is what we want the processing block to do. So if you remember previously, I had the input data, which is that green box, feeding into the yellow data, or the yellow box, which says processing. And the yellow box that says processing also had this thing called parameters, which was kind of feeding it. So it tells it how to process the data. Well, the model that I have here, which is this chain of dense things, it tells you how many parameters are inside of it and such. If I look at this model params thing, which I got from this flux.params function call, this represents all of the parameters. And it's not very user-friendly to look into this. And most people don't even look at this at all. But we're just taking a look here to kind of peek under the hood and see what's happening. These are the parameters inside the model that are going to be tweaked and are going to be improved through our training process in order to properly predict the next output. So,
a question, Elliot?
Go ahead.
Does the dense function apply a non-linearity? For example, rel u.
Yes, it does. That is a great question. And there's a little bit of subtlety here in that I have explicitly provided a what we call an activation function on the last one, but I've used the default one for the first two. Now, by default, the dense function, if we take a look at the help for it, it will give us all sorts of information about it. By default, the nonlinearity is going to be, well, it should be tan h or sigmoid. It looks like it says identity here. I think that's actually a bug in the documentation. But you can provide whatever kind of nonlinearity you want. By default, these should be using sigma, I believe. Let's go ahead and take a look. If we edit this, oh, well, that didn't work now, did it? Let's go ahead and open up this file. So the definition of the dense layer by default looks like it is an identity, actually. Well, that's actually a little surprising to me. All right, so what we're going to do is we're going to go ahead and apply a nonlinearity to these so that we have a nonlinearity on each step except for the last one. I don't think this is going to change the performance very much, but we're going to go ahead and see. So when we go ahead and chew through this, this chain, the inputs, which are 10 data points, are going to be multiplied by a 10 by 10 matrix, then passed through this nonlinearity, then fed off to the next dense layer, 10 by 10 matrix, past the nonlinearity, then a 10 by 1 matrix to output a single time point. And this one is not going to be passed through a nonlinearity because a nonlinearity kind of restricts the dynamic range that you can have on your output between 0 and 1, or between -1 and 1, usually for things like tan h. Or for ReLU, it can't be negative. For this kind of a task, we're predicting output, we want it to have full dynamic range. So we just want no nonlinearity on the end. All right, moving forward, looking into hyperparameters for training. When we're training, we pair the predicted output with the true output. We find the loss, and then we go and we alter the parameters. When we're altering the parameters, there's different ways to alter the parameters. The simplest way is using this thing called gradient descent, which is what most methods are based off of. But it's quite primitive. And there's newer, more advanced ways of altering parameters that have been developed since then. One of the gold standards is called Atom, and so that's what we're using here. This is called our optimizer. And Atom is the thing that will be responsible for taking the gradients that we've found and applying them to those parameters. Luckily, all of that complexity is hidden from us. Flux just takes care of it, and we're very happy about that. Atom does have a single parameter, which is called the learning rate. It's usually called eta. This is a number that when you make it smaller, the optimizer takes smaller steps. It modifies your parameters in smaller increments. And that can be useful when we're dealing with a network where when we try and modify the parameters, we modify it too much and we start doing worse. So this is one of those things where it's a little bit science and a little bit art to choose a good parameter value. if we have time, we'll train it a couple times and show what it looks like when you have too high or too small of a training parameter. We're going to learn to predict 15 time points in the future. So we're looking at the last 10 data points, and we're going to try and predict 15 data points into the future. And then we are going to keep track of which model performs best, and we're going to keep that one. Because sometimes when we train, we will, in fact, do worse after more and more training. So we want to keep track of which model did the best out of all the ones that we've trained so far. I'm going to skip over this for now really quick, just so that we can get a quick overview of the whole training loop. So I know it looks like a lot of code, but if we can think back to that flowchart that we had of taking input data, pushing it through the processing, calculating gradients, and updating parameters, it's actually not too bad. We're going to do this loop 1,000 times, and we call this each one of these iterations an epoch. In this case, an epoch is just a single run through of each data point. So we've kind of trained on the entire time series once by the end of an epoch. What we're going to do is we're going to take a window in time. So here I have a time start index that's kind of stepping forward in time. And we're going to extract what I'm calling X and Y, which is our inputs and our known output. And we're going to calculate Y hat, which is the predicted output. Our loss is the difference between Y hat and Y. And here, the way that we're calculating loss is just the mean standard error. It's a very standard way of doing a regression task where, mean squared error. And when we return L from this flux.gradient function, that's telling Flux, I want you to figure out how to reduce this number, make it go to 0 by changing these things. Now, if you remember, these model params are the pieces of data that we extracted from this model up here. And the beauty of Flux, and the thing that really makes machine learning a joy to perform in Julia, is that there's very little magic that's going on behind the scenes in terms of Flux figuring out how to change these parameters in order to reduce the loss. Well, I say very little magic, but what I really mean is there's quite a lot of magic because the Julia compiler is able to actually analyze the code and figure out how the loss is related to these model parameters by looking at the computation that's being done inside of this, when we call model on our data. This means that you, as the user, can write your own layers. You don't have to use the dense layer if you don't want to. Just 2 weeks ago, I wrote a layer that, instead of just doing matrix multiplications, it took the inputs and kind of multiplied them together to create polynomial factors, because I needed to do some modeling of something that really didn't have just a linear dependence on the data, it had a polynomial dependence on the data. And being able to write that and then have Flux figure out how the changes in those inputs are related to the parameters and how that's related to the loss. It's very powerful. It allows us to write an algorithm that processes our data without needing to manually specify those parameters, and then just use gradient descent and backpropagation. This idea of using Flux and program analysis to figure out, if I want to reduce this loss, how do I change these model parameters to do so? So we're going to take our batch of data, which we are getting from the stack data windows function, and we're going to pass it through the model to get our predicted outputs. We subtract it and square it from Y. We get a loss. We return that loss, which will give us gradients that are how we need to change the model parameters. And then we call optimize.update, where we have our optimizer, we have our gradients, and we say, change these model parameters according to these gradients by using the logic that this optimizer is built to perform. We'll do this over the entire time series. Then we'll keep on looping. Every 100 epochs, we will report that the epoch was done, and we'll also report what its loss was, which we are accumulating here. We would like to see, after epoch, the loss should decrease. In fact, we will push it onto epoch losses, and down here, we'll actually plot it so we can see what it looks like as it trains. If the current epoch loss is smaller than our best model loss so far, then we will save our best model. And we'll kind of keep track of the best one. All right, so let's go ahead and run this. Again, we are going to be looking at a window of 10 time points and trying to predict a point 15 time points in the future.
A question again, Elliot,
Yep.
if you don't mind. It's question is it possible to make composition? For example, compose the inputs with an LSTM before giving it to Flux and taking it into account in the feed forward?
Yes, absolutely. So you have complete control over how you process your data. So just to give a quick example, what I have bundled everything together into this chain thing, and I have this convenient flux.params function to get the parameters that I want to train on. But notice that all I'm really doing is calling model of x inside of this flux.gradient and passing the model parameters. So if I wanted to do some processing beforehand, I could do like pre-processing here, and that will work just fine. This will not be trained. Like any kind of modification of the data that you're doing in here, it's happening outside of the flux.gradient call, and furthermore, the parameters that you may have in here are not included in model parameters. So Flux won't pay attention to it. You can even put this in here. That's totally fine as well, because we're only telling Flux, these are the only things that you're going to calculate gradients on. Now, if you wanted to do something that also had gradients, if you wanted to calculate gradients on something that was not part of that chain, maybe you have a more complicated architecture where you have kind of two different models going at once, and then their outputs feed together into a third bigger model, et cetera, and you want to train them all specifically, yeah, that's totally fine. You can have multiple flux.gradient calls here where I'm training one thing over here, other model params. I do stuff here. And I have this thing update, I have that thing update, then the outputs of those feed into a third one and update that. You have complete freedom over what you want to do. Flux is pretty good at not forcing you into doing things a certain way. It may take a little bit of exploration to figure out how to use the different functions and the different compose the things together, but it is very composable. As I mentioned before in my thesis work, I actually ended up using a much earlier version of Flux to do some machine learning on cough sounds. And one of the things that we needed to do was to have an adversarial style network where we have one network that's trying to predict whether or not it's a tuberculosis cough or not. And then we have another network that's working against it that tries to kind of fool the network and strip information out of it in order to pare down the pieces of information that the network is allowed to look at. And in order to do that, we had to have kind of two separate optimizations going on within the same training loop. And it sounds very complicated, but once you get used to thinking about it as, oh, I'm just looking at the gradients imposed on these parameters by this loss, and then I'm optimizing that, having that fundamental down allows you to kind of very much more easily compose these complex or non-traditional learning frameworks or paradigms. Okay, so I finished training rather quickly, I might add, and it looks like we started at a loss of 240 and we dropped to a loss of 115. The absolute value of this loss has essentially no meaning. We like to call them engineering units. The value is very dependent on the scale of the data and your batch size and whatnot. All we really care about is kind of the shape that it makes as it goes down. So let's take a look at what the loss looks like. So you see we started up here and we kind of came down here, and it definitely looks like we've converged. Like we're not making much progress anymore. It's possible that if we reduced our learning rate, we would make more progress. But let's go ahead and take a look at what the forecasting looks like. So the way we're going to do this is we're going to collect X's for all of the time windows from the beginning all the way to the end of our data. And we're going to calculate that point 15 time points in the future, because time lag is 15, for each of those time points. Then we're going to take the actual outputs, and we're going to plot the difference between them. So that's what's happened here. And I'm going to zoom in again so we can see this a little bit more clearly. So the blue is the ground truth. It's what our actual input data is. Or actually, it's our output data. It's just shifted over 15 points in time. And then yellow is our prediction. And so you can see that we are in fact predicting something not too shabby. It seems like it's a little off sometimes. You can see it's kind of peaked a little bit earlier over here, whereas this peak seems to be much better. But overall, this is not too shabby. It doesn't quite get the high peak here, etc. But yeah, it's also quite wiggly, as you can see, and that is merely a function of the fact that the input is quite noisy. And so as we are only combining input values together, we would expect to get something a little wiggly at least. This doesn't really convince me that it's necessarily learned all that much, though. It's definitely learned the correlations. But one of the things that might be interesting is to ask, well, can we extrapolate, right? Given that it's looking at the last 10 time points and predicting the future one, what if we look at the last 10 time points of the things that we predicted in the past and keep on marching forward into the future? What would happen then? And so that's what we're going to do here. We're going to do the same thing up here where we feed in the inputs and get outputs for everything. And then we're just going to keep on feeding into the model the last analysis window length values and spitting out the next value. In fact, this actually shouldn't go back by analysis window. It should go back by analysis window and time lag to end minus time lag.
Elliot, it looks like
we're
you
looking
have
at 10 data points, but we're predicting 15 in the future. So we need to look back 25 ago. All right, let's go ahead and run this. And what
Elliot,
we get
there is a quick question. It looks like you've got it there on line 152, but it says, how would you model errors with this approach?
How would you model error? So the metric that I'm using when I'm training, and that is the most important question when you're dealing with a machine learning model, is how are you communicating error to the model? Because that's what it is going to try and minimize. So here I'm modeling it as the mean squared error between the prediction and the true output. So that means when it predicts a value here and the true value is here, it's going to take the difference, square them, and then it's going to try and reduce that, which means it's going to try and push this value close to here. Because it's mean squared error and not some other kind of error metric, this is going to behave kind of like a least squares fit. Once it converges, it'll behave like that. When I am extrapolating here, there's no way for me to calculate error, right? Because there's no ground truth for me to compare against. Did that answer your question?
Dario says yes.
All right, great, thank you. So we can see from our forecast that we actually get something that looks fairly reasonable in terms of a prediction. It's not perfect because it seems to be kind of decaying over time and such, but it at least shows that if we feed in the previous outputs and keep on going, we have figured out some kind of seasonality, right? Some kind of correlation between them. And so this is an example of us having trained a machine learning model, which does in fact understand some things about our model. Now for the really fun part where we start to mess around with parameters, right? We have something that kind of sort of works here. But of course, there's a lot of hyperparameters and design choices that I've made that change how this thing is going to behave over time, or change how it will behave in the real world. So just as an example, one thing that we can start to mess with is we can say, all right, we are predicting 15 points in the future from 10 points in the past, right? Let's make it a little bit harder. let's try and predict 25 time points in the future and only have, say, 5 points in the past. So when I do this, we get a new model value, which is 5, 5, 5, 5, 5, 1, etc. And then when you do this training, oh, I have to delete that pre-processing thing that I added. That doesn't exist. When I run this training, we can see that we started out at 370 loss and we dropped down to 172. That's a little bit worse than we did in the past. Even though the absolute value doesn't mean much, the relative value we know is different. If we look at the training, we still have converged. That's good. And if we look at the prediction, what we see is the machine learning model has completely given up. It's just, it thinks it's hopeless. It says, given those few inputs and trying to predict something so far in the future, I can't do it at all. It has absolutely no idea what to do. And so the best thing that it has figured out to do is to simply predict the average value. And that's how it minimizes the loss. So this is a good example of how it's doing its best to satisfy that error criterion, but it's doing something that we would consider to be completely unreasonable, right? This is not a very good model of our data at all. And so we may ask ourselves, what is the thing that broke it? Is it the analysis window length? Is it the time lag? Is it that I just have too high of a training rate, a learning rate? If I decrease the learning rate and try again, is it going to work better? My money says no. In fact, it'll probably be actually worse. Yeah, it's actually worse. So the answer in this particular case is the analysis window is too short. And the reason for that is if we look at only 5 time points, we're not going to be able to see very well where inside of a single cycle we are. 5 time points is just like 1, 2, 3, 4, 5, right? So this doesn't really give you much idea of the curvature of the input and output. And so it becomes very difficult for the algorithm to figure out kind of where it is in the cycle. As soon as I go back up to 10 data points, it should do much better, even though it's still trying to predict so far in the future. So we see our training loss comes down. That's good. And when we take a look at the output, yes, it looks much more reasonable. It's still pretty squirrely here. You can see there's quite a lot of noise now. And that's generally because the farther you predict into the future, the more difficult it is. But it's certainly a lot better than it was in the past.
2 quick questions, if you don't mind.
Yep.
So how would you handle the overfitting problem in Flux?
Yeah, that's a great question. So here we are explicitly not dealing with overfitting. In fact, we're trying to overfit, right? We don't have a separation between our training and our testing data. In a real world scenario, you of course want to be able to generalize this to new time sequences that you haven't seen before. And there are a variety of different ways of doing that. The most traditional and best way, of course, is to have a split between your training data and your testing data. So what that means is when I'm feeding data into our training loop here, passing X through the model, calculating Y hat, etc., I only do that on the training data. And I want my training data to be comprehensive enough that it captures all of the variation and richness of my data so that the model can learn everything that's going on inside the data. Then once I'm satisfied that the model has converged to the point that it's learned everything that I want it to, I will take the model and I will evaluate it on a new set of X's. And those X's come from data that I have withheld from the rest of my training group. And when I do this, you want the performance of your model to do well on these new pieces of data as well, right? Because for most machine learning tasks, we want to use the model on data that we've never seen before. And so this is kind of holding some data back in order to verify that it has stuff that it hasn't seen before. Now, Overfitting is the process of a model learning too much about the data that we trained on and only kind of working well on that particular data. And there's kind of a few rules of thumb to prevent that from happening. One is you don't want your model to have too many parameters. So in this example, this model is fairly small. It has 231 parameters. Now, if we're working on a real world task, say a computer vision problem, where we're taking pictures and trying to figure out if this is a dog or a fire hydrant, or if we're doing, speech analysis or something, we're going to have a lot more parameters. We're going to have tens, maybe hundreds of millions of parameters, and each of them is going to need to be trained. The more parameters your model has, the more expressiveness, flexibility it has. And when it's really trying its hardest to minimize this loss, it can do nasty things like try and memorize your data set, for instance, so that it sees some training data and it says, aha, I've seen this one before, and I know the answer is 5.5 or whatever. And so minimizing the number of parameters in your data set, or sorry, in your model, helps to fight against this kind of overfitting, because the model doesn't have the capacity to memorize. It has to kind of be generalizable. So the way to measure it is by having the test and train data split. And one of the ways to fight it is to have as small number of parameters as possible. None of this is specific to Flux, of course. This is just kind of general machine learning theory. And there are other ways of trying to do this as well. There's things called regularization that you can apply to your model that tries to force certain of your parameters to zero. It tries to kind of enforce sparsity, which is another way of trying to prevent it from just memorizing and overfitting. So that it kind of uses the bare minimum number of parameters as possible. Yeah, there's quite a few different ways that people try and prevent overfitting. And all of them are kind of machine learning theoretic. None of them are Flux specific.
Awesome, Elliot. And I don't know how far you are in the presentation. There's about 10 minutes left to the top of the hour. But we do have two other quick questions, hopefully.
All right, I'm just going to run the recurrent one while I answer those questions, because the recurrent one takes a fair bit longer to process. Go ahead, hit me up with those questions.
So how would you deal with unevenly sampled data?
Oh, that's such a great question. This is an active area of research that I'm very interested in. So unevenly sampled data or non-uniformly sampled data, I'm assuming you're referring to unevenly sampled in time. So correct me if you're wrong, but I'm going to answer that question first. Unevenly sampled in time. So this is tricky because, especially in things like, well, I'm going to switch back to my
Mario
notes.
says yes, by the way. It is. You are correct in your first assumption.
Great. So with something like this, the links between this node and the next node, these links stay the same once we're done training. And so if the meaning of x of t minus 1 versus x of t changes, like if the time difference between these changes, naturally you would think that the way the model has to deal with it needs to change as well. There are challenging problems like ones related to, say, differential equations, where there's some very, very fast changes in your system. You're modeling heat and someone lights a fire, and so there's a very quick change. But then once the fire kind of goes out, it changes very slowly, and so you'd rather kind of sample at very large time steps. The difference in the amount of time between your time points can cause big problems for these kinds of networks, because they kind of implicitly have this time delta built into them already. And recurrent networks are arguably even worse, because they may not have an explicit idea of time within them, and they have to reach backwards through many different time points, and so the issues only accumulate. And so one way to deal with this is to explicitly provide a delta t as an input. So not only do you give the value, but you also give how long since the last time point this value comes in. And that allows your network to kind of understand a little bit how it should evolve itself given this time point. The difference between I've gone from 0 to 1 over 1 second versus like on from 0 to 1 over 1,000 seconds, it will change how your network deals with it. There are more exotic and more interesting ways of dealing with this, though. And one of those ways is something that my coworker, Chris Rakakis, has really been pushing forward, which is neural ordinary differential equations, neural ODEs, we call them. And that's a way to kind of integrate an ODE solver into these kinds of neural network architectures, where you can basically have an ODE solver as a block inside of your neural network. And in fact, inside of the ODE solver, you can have neural networks that relate how the states are evolving. The reason why that's interesting is because the ODE solver is very good at dealing with nonlinear time steps. And so that's mostly useful for generating data. Like, you have a model where you want to generate a time series that is unevenly spaced. For analyzing, it's usually simpler to just give the time deltas as an extra input for each of your data points here. All right, and actually look at the chat here.
Yeah,
so,
you answered some of the ones that are most recent. So
yeah, can subsampling be implemented in a neural network? My question about composition on that purpose with OD solver else. Yep, yeah, composition with OD solvers. There's actually an entire what do you call it? GitHub organization that's dedicated to like composition with ODEs and stuff. If you look at the diffeq Flux package, the SciML and diffeq Flux places, these are great things to go to if you want to start dealing with things like differential equations and flux. And they have, in fact, tutorials that talk about some of these things. So if you go to the docs here, there's all sorts of tutorials on how to optimize these, use them on GPUs, deal with all sorts of different ways of training them, etc. So yeah, they've got an entire section on training techniques. So I highly recommend this. Depending on the data and its frequency, how to choose an approach to subsample it without using much predictability. Well, that may depend a lot on your data. In this example that I have over here, going back over here, I have just blithely subsampled. I've thrown away, 9 out of every 10 data points. And that's because I know that the data predictability that I'm depending on is very long term. If you don't know that, then you can't throw it away. You don't know. There's different ways of figuring this out. One is to analyze your data set, look at features, try and figure out what's important and what isn't. Another way is you have a machine learning based approach where you use like an autoencoder. An autoencoder is it's a neural network that takes your input and it squeezes it down to some smaller representation. Then it blows it back up into a larger representation, and it makes sure that this data is the same as this data. And if it can properly do that, then it has kind of correctly identified some kind of structure in your data and has discovered that this is actually the only information that you need in order to keep your all the dynamics, all the interesting stuff in your data. So for example, in our kind of sinusoidal looking data there's an awful lot of structure and just some noise. And so if we squeeze it down with an autoencoder, we could probably get a much smoother representation of it. All right, yes, spatiotemporal series, that's a whole nother webinar. But the basics remain the same. The main difference is that you would need to have a architecture that's doing something reasonable. And that's where we would get into things like convolutional layers and things like that. And then how to deal with multivariate input data. A single output time series with multiple input time series, it's actually quite simple. When we go back to something like, well, here we have our RNN, and here the RNN is taking in a single data time point at a time. I could just change this to 5, and it would take in 5 data points at each time. Looking at the feed forward one, where we have the dense layers, usually what you would do is you would stack the different pieces on top of each other. So maybe I would have, say, 5 times analysis window, and I just have to reshape my data to be a 5 by time points matrix into a single vector and feed it in. And then the dense layer would be free to learn mappings for all of those different data points. Similarly, if I wanted to have multiple outputs, I could just change this to 2, and I'd be calculating 2 outputs for each one. And then I would be responsible for defining an appropriate loss. And yeah, we did train a recurrent neural network here. I don't have time to go over how exactly we trained it, but we'll just satisfy ourselves that it's able to run. And unfortunately, I screwed something up with the stuff that I was changing there. So I'll have to, yeah, I changed a dimension when I was typing here. Oops. We'll try and train it one more time, but I think we're probably going to run out of time. Let's see if there's any more questions. Yep. So the RNN should give us a stable, forever oscillating output. I was kind of hoping to show that, and maybe I will be able to. Let's see. Yeah. So here you can see the RNN. It didn't train very well. You can see the loss is still quite high, probably because I changed something up there. But you can see that it is relatively stable, and it will continue to oscillate for forever. So I can put this to 2000, and it'll oscillate for forever, because the recurrent neural network has learned it in such a way that it's looking back and gaining just as much energy as it needs to from those previous oscillations. Whether that's a good thing or not is up to you, but yeah, there you go.
Elliot, I think we're gonna close this one out if that's okay with you. It looks like the questions have subsided here. You've done an excellent job. Certainly appreciate your presentation, Elliot.
Yep.
For the recorded version of this presentation and our past webinars, you can visit the resources tab at juliacomputing.com. For any help with your existing Julia use case, time series, machine learning, or other work in Julia Hub, please reach out to us at sales@juliacomputing.com. We'll be happy to help. Thanks again, everyone, and have a great remainder of your week.